Welcome back. After a series of reasonably long lectures, I thought we'll have a short lecture that will provide a nice balance also. The idea here is to cover a reasonable aspect related to a concept in one uh, class. Okay, so we have variable times. Some of my classes probably are only about 8-9 minutes. Some are reach about 20 minutes. Some 30. 20 is 20 to 30 is very common. Very rarely we go beyond 30 minutes. Today's class will hopefully be very short. I thought I'll introduce the friction factor for relative motion between a solid and a liquid. Okay. For a relative solid liquid motion, as I call it here, this will be relevant in many different situations. Solid moving through a liquid, which you may encounter in as a part of a biological system analysis, and so on and so forth. Okay. If you are looking at a macroscopic way of looking at it, mainly for design and operation, let us look at it this way. We'll also take some part of this later when we look at other more complex systems. Let us recall that the fluid exerts a force on the body of interest when it flows, and that force can be thought to consist of two parts: static force and a kinematic, having a static component and a kinematic component. A fluid, even if it doesn't flow, will exert a force on the body, right? That you know. And a hydrostatic pressure always exists. So the force due to that hydrostatic part is called the static force, and the force that is brought about because the liquid is moving is called the kinematic part, Fk. Fs, the force that is exerted even when the fluid is stationary, and Fk, the force exerted when the fluid is in relative motion compared to the body of interest. A is the appropriate area. Kinetic energy Ke dash is the kinetic energy per unit volume, and Fk is what is more commonly called as the drag force. Okay, and it is usually represented through a drag coefficient Cd. Okay, so when you have a Cd coming along, note that it represents the kinematic component of the force exerted by the fluid on the solid. For solids with a projected area of AP, okay, what is projected area? You take a solid, it could be of whatever shape, okay, let us take a sphere for simplicity. Then if you project the image onto a surface here, if it's a sphere, your projected area is going to be that of a circle. Yeah, this one projection is good enough to understand, okay. If you shine a light, whatever you're going to see is a circle. So the projected area is going to be that of a circle. This could be of whatever shape, and you could figure out a projected area which is appropriate to this shape. It could be complex, that doesn't matter. Okay. So that projected area is AP, the area projected on a plane that is normal to the relative motion direction. So let me revise that here. If the relative motion direction is this way, then this becomes the this becomes I was okay. This is the plane that is normal to the direction of motion. That's perfectly fine. So Fk is nothing but the area times half rho V infinity squared times the friction factor. Okay, so this is the friction factor for this situation. So in terms of the friction factor, the kinematic force is the area, the projected area, times the equivalent of a stress, half rho V squared, rho V infinity squared, times a friction factor for this case. 3.9.2-1. V infinity is the free stream velocity, which is also called the approach velocity at a large distance from the object. Near the object, the velocities could be different. When the fluid is not under the influence of the solid, whatever velocity it has, that is called the approach velocity or the free stream velocity. Now let us say that a sphere is falling through a fluid at its terminal velocity. This is something that you're very familiar with. Okay, all the Stokes law and things like that situation have been derived using this scenario. The sphere is falling through a fluid at its terminal velocity. The projected area of the sphere, it's falling, the area, the direction that is normal is this, the projected area is whatever is projected onto that plane. That would be a sphere, of course, that would be a circle, of course. Therefore, the AP is going to be pi r squared or pi d squared by 4. The terminal velocity you all know, or let us represent the terminal velocity as Vt, and let us say that it is equal to V infinity. And the density of the particle is rho p. The density of the fluid is rho. And if you do a force balance on the particle under these conditions, you know the force balance, right? There's a gravitational force here, there is a buoyancy force in this direction, and there's a drag force in the direction opposite to that of the motion. All these would give you the Fk as the difference between the gravitational force, 4 by 3 pi r cubed is the volume times the density of the particle is the mass of the particle. Mass of the particle times g is the weight, the force of the gravitational force on the particle, minus the buoyancy force, 4 by 3 pi r cubed, the volume times the density of the fluid times g. That will act in the opposite direction. We all know this. Equation 3.9.2-2. And from this, from 3.9.2-1, we get this expression for the kinematic force, the projected area pi r squared times half rho Vt squared times the friction factor. Therefore, the friction factor, if you these two are the left hand sides are the same, therefore you can equate the right hand sides. If you equate the right hand sides, we get the friction and simplify. I'd like you to do that. It's quite straightforward. This minus this divided by this essentially will turn out to be 4gd diameter divided by 3 Vt squared rho p minus rho by rho. Okay. So we have a friction factor, equation 3.9.2-3, for this case of a relative motion between a solid and a fluid. Okay. I thought I'll just tell you this and make it a short class, okay, so that there is some sense of balance in terms of time. Okay, see you in the next class then.